Welcome to A&P Live Studio. I'm your host. As a registered nurse and an anatomy and physiology instructor for advanced healthcare professionals, I get to talk about some really fascinating topics. And today we're getting into one of the most important ideas in all of pain science, the gait control theory.
So let's start with something we've all done. You whack your elbow on a door frame and without even thinking, you start rubbing it. And somehow, it actually feels better. Now, this isn't just a trick of the mind. There's some really elegant neurophysiology happening under the skin, and that's exactly what we're going to unpack today.
All right, so here's our game plan. First, we'll cover the basic wiring for how pain signals get from point A to point B. Then we'll dive into the gait control theory itself. After that, we'll see how the brain gets involved with its own top-down control. And finally, we'll connect it all to real-world treatments and, of course, what happens when this whole system breaks down.
Okay, so before we can even talk about how to control or modulate a pain signal, we first have to understand the standard route that signal takes. So let's begin with the body's fundamental alarm system. Now, this is where things get really interesting. You can think of your sensory nerves like a highway with different speed lanes. You've got the A-beta fibers in the express lane. They're huge, wrapped in lots of myelin insulation, and they are super fast. They carry gentle information, like light touch. Then you have the A-delta and C fibers. They're in the slow lanes. They're much smaller, less insulated, and they carry the pain signals. This difference in speed? Well, that's absolutely crucial. It's the key to this whole puzzle.
So here's the typical journey of a pain signal. It's like a three-part relay race to the brain. It starts when nociceptors, your pain receptors, get triggered. That signal zips along the first neuron to the spinal cord. There, it hands off the message to a second neuron, which crosses over and heads up to the thalamus. And finally, a third neuron takes it the rest of the way to your cortex, which is when you consciously think, ouch. This is our baseline, the standard uninterrupted alarm bell.
Now that we've got that standard pathway down, we can introduce the main event. The gait control theory is what gives us that beautiful, elegant explanation for our original question: why does rubbing an injury actually work?
This idea was proposed way back in 1965 by two researchers, Melzack and Wall, and it was nothing short of revolutionary. It completely changed our view of pain from being a simple one-way street to this dynamic process that the body can actually control. And while it's been updated over the years, the core concept is still the foundation of modern pain science.
Okay, this diagram shows it all. When you get hurt, those small S fibers, the pain fibers, do two things at once. First, they tell the transmission cell, or T cell, to send a pain message up to the brain. But, and this is key, they also tell an inhibitory cell, the SG cell, to be quiet. You can think of that SG cell as the brake pedal. So the pain signal hits the gas and takes the foot off the brake, essentially flinging the gate wide open for the pain signal to rush through.
But now, here's the magic. This is the aha moment. When you start rubbing that spot, you activate those big, fast L fibers, the touch fibers, and they do the exact opposite. They race to that inhibitory SG cell and tell it to get to work. They basically slam on the brakes. This powerful inhibitory signal blocks the T cell from firing, so that faster, non-painful touch signal gets to the gate first and shuts it down, preventing the slower pain signal from ever reaching the brain.
But wait, the story doesn't just stop at the spinal cord. Your brain isn't just a passive audience member in all of this. It's more like the director of the show. It has its own powerful top-down control system. Think of it like a master volume dial for pain.
And this pathway you're seeing here, the PAG-RVM system, is that volume dial. Your higher brain centers, the parts that deal with emotion, stress, and expectation, can activate a part of the midbrain called the periaqueductal brake, or PAG. The PAG then sends a signal down to the RVM in the brainstem, which then sends its own messages all the way back down the spinal cord to influence that very same gait we just talked about. It's how your psychological state can literally turn the volume of pain up or down.
And how does it work its magic? Well, it's all about neurochemistry. These descending pathways release neurotransmitters like serotonin and noradrenaline, which act as brakes on the pain signal. This is also where your body's own natural painkillers, your endorphins, come into play. And by the way, this is the exact same system that powerful opioid medications are designed to activate.
So let's bring this out of the textbook and into the clinic. Understanding all these mechanisms isn't just an academic exercise, it's the real-world basis for so many of the pain management strategies we use every single day.
We can actually sort our treatments into two main groups based on this theory. First, you have therapies that work by stimulating those large fibers to close the gate locally, right at the spinal cord. Things like a TENS unit, massage, even just a heat pack. Then, you have the treatments that work from the top down, by activating the brain's own descending pain control pathways, like opioids or even psychological techniques.
A TENS unit is a fantastic, real-world example of the gate theory in action. It uses a mild electrical current to specifically target and stimulate those large, fast A-beta fibers. The whole idea is to send so much non-painful touch information down the highway that the pain signals from the smaller fibers just get crowded out and the gate closes.
Now, we've seen how elegant this system is when it's working right, but we also have to talk about what happens when it breaks. When the gates or the descending controls stop working properly, it can lead to some really difficult chronic pain conditions.
And neuropathic pain is a perfect example of this. This isn't just pain from a cut or a bruise. It's pain caused by damage to the nerves themselves. If we think about our model, it's like the inhibitory gatekeeper cells have been damaged or aren't working right. The gate basically gets stuck in the open position, allowing pain signals to fire wildly and uncontrollably.
And this is why the quality of that pain is so different. You could see here that typical nociceptive pain is pretty localized to where you got hurt, but neuropathic pain, it tends to follow the path of the specific nerve that's damaged, which is what causes those classic radiating, shooting, or burning sensations.
So what's the big picture here? What is the lasting impact of this theory? Well, the greatest legacy of the gate control theory is that it fundamentally changed our entire model of what pain even is, moving it from a simple alarm to a complex personal experience.
And this quote just says it all. Pain isn't just a raw sensation traveling up a wire. It's a full-on experience that is deeply shaped by our minds, our emotions, our past experiences, and our beliefs about it. The gate theory gave us the neurological framework to finally understand how that was possible.
And all of this leads directly to the modern biopsychosocial model of pain. For anyone going into healthcare, this is such a critical concept. It reminds us that we can't just treat the biology of pain. We have to see the whole person, their psychological state, their social environment, because all of these things are interacting to create their unique experience of pain.
So, to wrap it all up in a nutshell, we have a basic pain alarm system carried by slow nerve fibers. But, critically, there's a gate in the spinal cord that can be closed either by faster touch signals coming in or by top-down control signals coming from the brain. This simple, elegant idea explains everything from why we rub a bump to how advanced therapies like TENS and even opioids actually work.
And that leaves us with a really important question for the future of healthcare. We know neurologically that our thoughts and emotions can physically alter pain signals. So the challenge for all of us is this: how do we do a better job of integrating cognitive and emotional therapies into our standard pain management plans so they're not just an afterthought?
That's all we have for today. Stay patho-curious, and I'll see you in the next episode. And just a reminder, this video is for educational purposes only and is not intended as medical advice.